I have an opinion that's somewhat controversial.
All right, let's do it. As long as you're willing to post this to millions and millions of your fans online.
Well, here we go. So my opinion is that people should learn to program before they learn statistics, and that when we teach statistics to people, we should assume they know how to program and take advantage of that.
Interesting. So programming before statistics.
Yes.
So there's no calculus anywhere in sight, I assume. That's already blown out of the water.
Actually, a lot of statistics courses expect you to take calculus first. And that's because the techniques that you end up using when you don't have a computer require a lot of calculus. But if you do have a computer, the need for calculus is substantially reduced, even at least for the kind of introductory material that you see in statistics.
Right, right. So I saw a recent talk by this UW guy who's the statistics for hackers, Jake Vanderplas, I think. He gave this talk at like PyData or PyCon actually, and he's this like e-science, open Python kind of guy, and he basically just gave this tutorial about like, here's like a bunch of short Python script you can write to implement common statistical approaches, and here's how you get intuition about what a t-test is, what a binomial test is, and stuff. And it was just all very iterative, imperative, and algorithmic instead of like, here's a giant declarative math formula you have to memorize.
Yeah, so I think that's a big part of the motivation, is the same reason why when you're learning to program, you should actually write programs instead of just staring at them or having someone tell you that they work, you want to run them. That if you implement a statistical procedure or any kind of data analysis procedure, you get to really believe that it works because you get to try it out.
Mm-hmm. And you get to debug it too, right? You get to debug it on real data and see where it goes wrong, and get intuition about it.
And like the most common thing that's asked in a statistics course by the brave students is, why is the technique just the way it is as opposed to something slightly different? And I know that's just like a broad statement, but it's true for many specific instances of whether you're doing hypothesis testing or confidence intervals or whatever. There are details that the students are expected to memorize, and one could imagine they could be different. Well, without a computer, you kind of have to either trust your instructor that it just is the way it is, or maybe they'll tell you, oh, it could be either way, it doesn't matter, but that's very unsatisfying. Yeah. Or you can, try to apply some calculus and, work through some asymptotics of how this thing might behave, and you might learn something that way, but that's usually beyond the scope of what someone can do if they're just learning statistics. So you're basically stuck. You can't ask the question, what if we tried something slightly different? Would it still give us the same answer? What if you have a computer? You just try it.
Yeah, this is super fascinating. I have a bunch of low-level detail questions about this, but I guess we should start by going super high level. And what prompted you to make this statement at this point in time?
So statistics is still taught almost everywhere, including Berkeley, as under the assumption that you know algebra, you might know some calculus, you have a calculator, and you kind of know how to use that calculator, and you certainly don't own a computer, or if you do, you might be able to open up Excel and run some like pre-canned visualization in Excel, but you don't know how to program it. So it's just like state of the world right now is that people are teaching statistics assuming that people don't have computers, or if they do, they don't know how to program them. And so last year we taught a course that made the other assumption, that people should learn to program before they learn statistics. We packed it all into one freshman level course. So
right. So give a bit of background about that.
So this wasn't my idea. This was originally kind of out of Mike Jordan's head, is that he wanted to teach statistics well to lots of people, and that would involve some computing. But he got a group of people together at Berkeley, and we all talked about, what would be the right place in someone's education for them to get exposed to the intersection of statistics and computing. Because at the research level in statistics, there's lots of computing. So if you think about like, oh, it should be in their PhD if someone's working toward a PhD. Well, what about the master's level? Yeah, in any kind of advanced statistics, there's a lot of computing, so it should be there too. But then we started thinking about it, and it seemed like from the very beginning of when you're trying to learn about data analysis, there should be computing there, because you could use techniques that were more intuitive, you could do more explorations, you could try stuff out on real world data. So it shouldn't be like a master's level thing or a PhD level thing or a senior capstone course level thing. It should be a freshman. You show up on campus, you want to learn about data, you should learn about it by learning a little bit of computing and then applying that to data analysis problems. And all of a sudden you start running into statistical questions. So then you want to learn some statistical techniques.
Cool. So this is a freshman class at UC Berkeley, and how this was offered once or twice before, and how big is it?
Yeah, so the course is called Data 8. You can find it at data8.org, or the long name is Foundations of Data Science.
Why
We
8?
offered it, huh?
Why 8?
Oh, we just needed a number, and we needed to pick a number that wasn't taken in several different departments, because it's actually cross-listed in computer science, statistics, and the information school. And it turns out that, like, 10 was used in computer science and 2 was used in statistics. So
you got a domain name too, which is cool.
And data8.org was available, so that was good. Yeah, so that's how we got the 8. And yeah, we offered it twice. I normally teach intro computer science, which is required for being a computer science major. So tons of people take that because they want to be computer science majors. This course doesn't really count for much. I mean, now it's starting to count for people's statistics requirement and economics and stuff like that, because we teach enough statistics that those other departments have started accepting it. But at the beginning, this was basically a course people were taking out of interest, and yet a bunch of people signed up anyway. So we had 450 people in the course when I taught it last semester. The pilot offering had about 100, because we just restricted it to freshmen, and we didn't, no one knew what it was or whether it was going to be good. So, 100 brave freshmen showed up, which was cool.
And is it all freshmen still, or is it all years?
No, we let everyone in. So it was 45% freshmen out of the 450.
So it's much like, I mean, based on the, freshman heavy enrollment, I mean, this is posing as sort of an, I guess we can transition this, since you teach the giant intro class at Berkeley. This is sort of another, if this is maybe the only intro to programming that a lot of non-majors get. So I guess I want to brainstorm about how much programming do they need or want to learn before they can get to doing the statistical stuff? This kind of this chicken and egg problem. They can't go through a ton of programming, but they can't do none either. So how much in detail do you go on the Python programming part, in addition to doing all the statistical stuff?
Okay, let me start. Let me take 2 steps back and give some motivation for what I'm about to tell you. So computing really has 2 purposes in the world: building stuff and studying the world. Most computer science curricula are built around the how do you build stuff problem, which is great. And that includes our intro CS course. Well, I mean, we kind of have a 2 or 3, depending on how you count, semester introduction to computer science, where you're building stuff over and over again, and the things you build are more and more complicated. But they don't involve a whole lot of studying the world. I mean, they're really about, what can you do when you're building a computer application. The studying the world part of computing touches a lot of different disciplines. So it's not just computer science alone, but it tends to exist at the intersection of computer science and natural sciences and social sciences and stuff like that. And it involves a lot of data analysis, of course. And that does involve kind of a different set of, a different kind of minimal set of computing ideas that you need in order to be productive. Because the core of building things, which is all about abstraction and control flow and handling inputs and, programs that evolve over time, they don't really show up when you're just studying a table full of numbers. What does show up is table manipulation. So that's really core for us. So you get like arrays of numbers, or you get tables full of numbers, which is a bunch of columns all kind of glued together, or a bunch of rows, depending on how you view it. And part of computer science is how you manipulate tables. So what's relational algebra, and how do you join 2 tables together, and how do you filter them, and how do you take one column of numbers and map it into another column of numbers, and how do you reduce them into a single statistic and stuff like that. So that's the piece of computing that we teach. is if you have a list of numbers or two lists of numbers or a table full of numbers and categories and things like that, how do you manipulate them in order to get the table you want from the table you got?
Right, and you're still using something like Python or like an imperative language rather than a spreadsheet or a front end for a database or something. It's like you're still writing straight line imperative code for doing these sort of relationally table-y operations.
Yeah, so I like languages that are not just Turing complete, but make it easy to do lots of different things. You know, if you want your program that's just about data analysis to later evolve into a web application, it should be like pretty straightforward to do that.
Right.
I'm
yeah.
happy to teach in Python just because it, you know, supports a lot of different kinds of programming.
Yeah, and the talk that I saw about this, it's called Statistics for Hackers, and I think one of the things I gleaned from that talk was that by explicitly doing iteration and doing a doubly nested for loop with some random numbers and stuff, you can get an intuition about here's how we do Monte Carlo sampling or something. We're literally just doing random, and then seeing how many percent of the time it hits and then binning it or something. And it's much more explicit than, say, some like, I don't know, some like Prolog logic program or some gigantic declarative SQL statement that you don't have much intuition about. So that, it's less pure in terms of the programming language perspective, but it's more explicit out there for novices of just, here, I'm going to follow you. Here's a loop. We're going to keep doing this 10,000 times, and here's the distribution of stuff we get.
Yeah, no, I think that's exactly right. Like, the wonderful thing, but the crutch that's involved with Prolog and SQL is that the programmer doesn't have control over what happens at execution time, right? It's supposed to be the environment that figures out how to compute whatever result you declaratively specify. And that's awesome if all you want is the output. But if you want to trace the execution of the program in order to understand what's going on, if you want to like stick in a print statement somewhere to see like what are the intermediate steps, then it's better to write out the procedures in an imperative language where you have full control over everything that happens.
That's interesting. So do you do recursion at all in this sort of class, or is it all just kind of more straight line imperative code?
Yeah, we don't do any recursion. We don't do any structured data. So by that I mean like tree structured data, any like object that has attributes, and those attributes can be objects. That's all beyond the scope. There's
right, because that's
lots of information out there that can be represented as a table.
That's right.
And so it's not true that everything can be represented easily as a table. I mean, yes, it can technically, but that's not how you would do it if you were solving lots of different problems. But for a huge class of problems, tables are sufficient for representing whatever you want to represent in the world, exploring the data, doing any kind of manipulation where you discover something that you didn't know before by processing the data. So yeah, so we skip trees and dictionaries, and it's really just arrays, which are like lists, except for that you can do arithmetic on them more easily. And there's still a lot to learn. So so it's not like we run out of computing topics, statistics topics to learn in this, to teach in this semester. I mean, it's really packed with stuff, even though we teach a much more limited set of the computing ideas than you'd see in a typical intro CS course.
Yeah, I mean, I think this contrasts in my mind with your CS61A intro, which is very much about recursion and structure and very classic computer sciencey principles, which is actually really different than the sort of flat table iterative sort of methods you need for data science, right? I mean, for lack of a better term, for data sciencey things are usually flat and tabular for the most part, and then these computer sciencey stuff that you want to learn to say, like, how do I build a programming language, or how do I build the next compiler, or an operating system scheduler, is usually more structured and recursive and nested. What are your thoughts about semi-structured data? So one of my things is I notice colleagues in other fields, in non-computing fields, a lot of their data analysis and processing is surprisingly linear, as you notice, right? Like it's just a list of a time series or just a table of stuff. But when I'm doing a lot of log analysis or data munging on stuff, a lot of times it is nested, right? You're getting some JSON blob back from an API, or you're mining some log data and there's some weird nesting and you got to move stuff around. So do you feel like that's outside of the scope of what data scientists would need for the intro, is too complicated, or do you feel like there's some place for that sort of semi-structured, messy, nested data.
Yeah, I mean, you can't ignore it forever, right? There's lots of nested, structured data that the most typical way of processing it is turning it into a table and then using your kind of table-based tools in order to process it. But you got to do that work, and that work involves writing programs. Yeah, we don't teach it in our first class, but we're building a kind of second upper division data science course that will certainly include how do you apply these ideas to structured data.
Right. And so the first class, you're assuming all the data sets are clean then, like you're giving them clean data sets.
Yeah, I mean, how clean are they? There's lots of tabular data in the world that's not very clean, but it's not clean. It's not messy because the structure is wrong. I mean, the table is there and has the right number of rows and the right number of columns. It tends to be messy because of the actual values. So, there might be missing values, which we try not to talk about too much. But even when there aren't missing values, there's just weird outliers that would kind of confuse any kind of naive analysis. And you got to look at those.
And is that part of the lessons of, we have some weird outliers, or we should use statistics or whatever that's more resilient to outliers and stuff?
Yeah, or, we should visualize our data before we start applying some fixed procedure to them to make sure that the assumptions that we've made in the procedure actually apply, and that we're going to learn what we want to learn instead of something else. Right.
So going back to the high level topic that you started with your assertion that people should learn programming before statistics. What about, so I guess another way we could branch off a lot of directions. So what about you're obviously much more experienced at the college level, but what about even at the high school level or before, right? Because there's all these people grumbling about the traditional math curriculum for 100 years, like, oh, we got to learn trigonometry and calculus. But, what can you imagine as a more modernized, ideal high school mathy curriculum in this worldview?
Oh, great question. I still stand by my assertion, even at the high school level. I don't think statistics, inferential statistics needs to come very early in your education. Programming could come really early. That would be great because it's useful in lots of different settings. I feel like it's often the case that probability is taught before statistics. So probability is the random process and you're predicting what comes out.
And is probability, do you see the programming being involved in probability, or is that just crunching through math?
Programming is great for probability because you can prove that you're right just through simulation, but it's not a hard prerequisite in the same way that I feel like it is for statistics. Because you can learn a lot about probability just by, learning the rules and applying them, and you can carry out simulations just by flipping coins and building a roulette wheel and rolling it and stuff like that. I mean, you don't necessarily need a computer to run the simulations. It's nice to have, but it's not necessary. And getting kind of experience with random stuff through probability, where you kind of know how the random system works, and you want to say something about what's going to happen when you sample from it. That's probably a good place to start, and that shows up in pre-calculus courses, I think. And then statistics, which is the other way around. You have a sample and you want to understand the population, or you want to understand the random process that gave rise to that sample. Really probably should come later. I mean, the ideas are more subtle. There's so many ways in which they can be misunderstood. It's not the case that the computation is all that hard in like an intro statistics class, but correctly interpreting the result, like, oh, I've built this histogram, what does it mean? Or I've run this hypothesis test, what does it mean? Or I've computed this confidence interval, like, what does that actually say? This kind of stuff is not really like high school level material. I mean, yes, there are tons of high schoolers in the world who can grasp it, but you don't really need to until later, because you have to care about studying the world before you learn this stuff, and it is really pretty subtle. I've grown a stronger appreciation for how hard like basic statistical concepts are to state correctly, because I've had to stand in front of a lecture hall and make sure that I don't say the wrong thing, and so that's kind of led me to believe that statistics isn't something that you should be learning as a freshman in high school or a sophomore in high school. Maybe as in kind of AP course, or maybe in college.
Yeah, that's a really good point. I mean, I took AP statistics as like my senior year, and it was a pretty lightweight course, right? It was like a half semester or something like that. Or I don't remember how big it was, but it was like super, super lightweight as a course. And it was just, here are some formulas and study for the AP test. And there was obviously no programming or anything back then in it.
Yeah.
So I guess to wrap up a bit, what are your thoughts about, so, maybe a more extreme stance that we can try to think about is thinking about your data 8 class is your kind of data-oriented programming versus computer science-oriented programming. Would you push that more on CS majors, as in, would you claim that freshman CS majors should learn this sort of programming first versus the, we're going to do a recursive descent parser in Scheme type intro CS first? Or do you still, stand by the original way?
I actually don't care that much about the order, but I do feel like most people should be exposed to both. If you're getting into computer science because you just want to build stuff and you don't really care about studying the world, well, then maybe you don't need a data science course. You don't need to study any statistics. But we do see a lot of students that are interested in computer science because of the effect computing will have on the world. Kind of the norm, I would say. And so all these people should get more experience pulling in a description of the world as data and figuring out what it tells them about the world. Because most data that you find is just a sample of what's really going on. It's just a snapshot of one little piece of the world. And if you want to say something about how the world really works or what's going on there, then you need some statistical techniques. So okay, so then there's the question of order. I think for the best thing I can imagine is that you take data science first, where you learn to program, but you don't learn a lot of a programming language, just enough to do interesting stuff. And then you do that interesting stuff over and over again for a bunch of different problems. Now, there's got to be something new happening while you're practicing. Otherwise, you get bored. And that new thing, in our case, is that you learn different statistical techniques. So this is kind of like fixed core of computing techniques, and now you're applying them to different settings. Like, do I want to do prediction, or do I want to do inference, hypothesis testing? Do I have, am I comparing two different samples, or am I just analyzing one sample? All these different steps that you go along the way. And by the end of that, you haven't learned a whole lot of computing, but you've gotten really confident about the parts that you've learned. And then you're kind of ready to go deep into a full survey of everything you should know in computer science, which is what our intro CS course looks like. And you can learn to recurse through trees and build interpreters and all that cool stuff. But if people want to do it the other order, it's fine too.
Yeah, I mean, this is we're talking about a big thing about CS education now is this multiple pathways into CS and out of CS, right? That it's much traditional computer science, the SICP model is very this clean mathematical self-enclosed world of this is some beautiful land of scheme that you're entering, and we're gonna compute in here, and it's awesome. And more and more now, there's been curricula and movements about bringing CS plus X, right? Bringing CS into other world and bringing other world into CS. And this thing that we've been talking about for these 20 minutes is really embodiment. I mean, to me, we started this conversation about statistics, but really, that term, I still struggle to find a good term for this, but I like your framing of using computing to understand the world, right? You don't have to use a t-test. You just have to understand a methodology by which you use computers to process some data to generate some knowledge. And we still struggle to come to a good, data science is the best, most widely used term people have, but I still struggle with that, what do you call that thing? Like that programming for understanding the world versus programming to do software engineering. So I guess, do you have thoughts about better terminology for that?
It's really hard to name these things. So I haven't tried, other than to say like, you either build stuff or you study the world.
Yeah, I like
That's as far as I've gotten. But those two are really different. And of course, there are applications that do both at the same time. But they basically involve different techniques.
That's right. And you know, the basic programming concepts are the same, but I think that you can imagine building up a kind of a knowledge hierarchy of what you should know about programming, and it probably diverges pretty early, right? Like you should know like basic tokens and syntax and typing, but then, you know, on one end you probably have to learn more about recursion and object-oriented stuff, and on the other end you want to learn more about just functions and, you know, multi-dimensional array syntax.
Yeah, basically it diverges after 2 weeks.
Right. Yeah, my undergrad advisor, who's at UW now, Mike Ernst, he taught this class he called it data programming. So this is before data science was a thing. So that was kind of his attempt at naming this. And I think a lot of people are trying to triangulate on this concept. But I think we're going to see more and more of this. So at UCSD, we have one of my colleagues in cognitive science teaches like the intro data sciencey course, and I should talk with him more about his philosophy, because he's like a neuroscientist, right? He's like a computational scientist who does all the Python notebook stuff, and he does the, you know, the data 8 type equivalent. I don't think it's as much focus on, you know, teaching statistics, but it's more on, you know, how do you get aspiring scientists in all fields to get up to speed on programming. So this is obviously super, super fascinating. So final parting words or punditry.
Yeah, well, I guess my final word will be a response to what you just said, which is that to me, this new material doesn't replace intro computer science. It's a complement to it. And so there's like more interesting stuff to learn, and you don't have to reorient all of your computer science curriculum to something new in a data-rich world. You just have to teach this other thing too. Good,
I like this. That's a very diplomatic answer that protects the future of your job and the jobs of everybody teaching CS1 courses. I like it. It's expanding the pie rather than replacing it. I like that.
It really is. Cool.
All right, awesome.
Well, this is super fun.